what I thought I would do is take a look at exploring CO2, carbon dioxide, as a refrigerant. What are our typical refrigerants? R134A, ammonia. But you'll see more of CO2 being considered as a refrigerant because of why? Because it's these other gases or other refrigerants have environmental concerns, okay, for greenhouse gas, okay, and ozone depletion, but primarily greenhouse gas. Also, CO2, if it leaks out, it's okay. But let's explore it as a refrigerant using RefProp. So last time we were introduced to RefProp, let's go ahead and open it up. So here's RefProp, right? And you can come in and you can select your units. And here we have it in English units, so degrees F and PSI, PSIA and BTUs. I like to think in degrees F, so what we'll do is we'll work in these units, okay, not SI. And what we're going to do is, I should back up a little bit. I should say, if you are going to use CO2 as a refrigerant, would you have a compressor? Would you have some sort of heat exchanger which rejects heat, known as the condenser, then some expansion valve, and then some heat exchanger like an evaporator, where you pick up some heat and go back and forth, like a cycle, 1, 2, 3, 4 for our states in between. Makes sense? And we have a high pressure side, pressure high, and we have a low pressure side, pressure low. And if, let's say, you want to make ice with that, right? You probably want the fluid in the refrigerant to be coming out, let's say, around 0 degrees F, such that there's maybe a delta T in the evaporator of about 15 degrees F, meaning that it can keep something cold at around 15 degrees F, okay? I forget the temperature for a lot of the frozen products, but it's probably 10 degrees F. Ice cream, I think you try to keep it around 10 degrees F. So you would be passing maybe air over this evaporator coil, and that air would be coming out at around 15 degrees F, 15 degrees higher than 0 degrees F. And maybe it would pass through the room that you're freezing the product in, and maybe it would pick up another 10 or 15 degrees and come back. All right. Out here, we have some other air coming across, and it's up on the roof, the condensing unit, and it's a hot day, and you still want to have ice cream or ice inside your warehouse, and so you have to reject heat to, I don't know, 125 degree F room, or air. Not room, but it's maybe rooftop air. And so the temperature that this condenser is going to work at, if you have a delta T of about 15 degrees F here, is the refrigerant in the condenser has to be higher. True? So it has to be what, 140 degrees F. So if your refrigerant is 140 or greater, it'll push the heat out and make the hot air outside on the roof even hotter. So you kind of get a sense of these real delta T's that exist to make the heat transfer occur. So keep in mind something like 0 degrees F and 140 degrees F, okay, as our minimum and maximum temperatures, as we talk about CO2 as refrigerant. Let's jump into here now. What type of plot, we know we're going to work in degrees F, PSI, BTUs per pound, but what type of plot would you like to do to explore CO2 as refrigerant? temperature entropy, temperature enthalpy, pressure, what is D, density? No, yeah, that's probably density, or PV type of plot, pH, pressure density, pressure specific volume, pressure temperature, ZP. Boy, I'd have to go and look at exactly what type of plot they have. Is that the compressibility factor, Z? Maybe. Okay, I haven't plotted all these. How about a pH diagram? Pressure enthalpy is very common. Why? Because we have a high pressure side and a low pressure side. Now, we can range the temperature from maybe negative 60 degrees F, which seems a little excessive, up to 300. So maybe just negative, I don't know, well, negative 40, up to 300 degrees F in 20 degree increments. The x-axis in BTUs per pound looks reasonable, and the y-axis looks like it's going to go way up there to 30,000 psi. Maybe I don't need 30,000 psi. How about just 10,000 psi, huh? Right? I'll leave 30,000, fine. How about lines of constant entropy? Looks like they're recommending some and showing it through the two-phase region, and connect saturation states, so it connects lines in the saturation states in the two-phase region. Let's see what they give us for a plot. So here's a plot. Let's see if I can expand it a little bit and take a look at it. It's a pressure enthalpy plot for carbon dioxide. On the y-axis, pressure in psia. On the x-axis, enthalpy. We see the dome, true? And let's take a look. If you wanted carbon dioxide to be in the two-phase dome at 80 degrees F, roughly what's the pressure? It's about 1,000 psi, true? That would be the saturation pressure. How about at 0 degrees F? It looks like the saturation pressure is around 300. Just eyeballing it, coming across 300, true? So what we can do here is we plotted these lines of constant S. Why did we plot lines of constant S? Because in our traditional vapor compression refrigeration, what comes out of the evaporator is saturated vapor, somewhere along here, saturated vapor, right? And if you had a great compressor, it would be isentropic. It would follow a line of constant S going up. That's why we put a nice line of constant entropy on this pH diagram. So if you would think, maybe we want to think, okay, it's going to come out 0 degrees F, and let's say it comes out saturated vapor. I put it through the compressor. It goes along a line of constant S scooting up this way. And depending on how far I want to go, because this is a line of constant pressure, true? Horizontal. What are these other lines? These lines are constant temperature. So 0 degree F comes across, then scoots down. And this one is 0 degree F scooting up like that. Okay. What is this line way out here? That's a 300 degree F isotherm. True? That's 300 degrees F. This one's 280. This one's 260. So we're going to have to increase the pressure to get the temperature of our CO2 high enough to reject heat in the condenser. Yes?
What is the constant, the constant temperature curve, I guess, not act as a real function across enthalpy? How it goes as it increases in pressure.
If you go,
there's a point where the enthalpy decreases and increases again.
Okay, where does the CO2 behave as an ideal gas? And when it behaves as an ideal gas, the enthalpy is a function of temperature only. So where in this plot is enthalpy a function of temperature only? I'm rewording your question, okay? Is that okay? So where on this plot is enthalpy a function of temperature only? Is it out in this region? No. No. Not in that region. Where's it at? Definitely not in the two-phase region. It's where the line of constant enthalpy, straight up and down, is consistent with the line of constant temperature, and the temperature being straight up and down. So it would be out in this region, or wherever you have where the lines are straight up and down. For, constant temperature is that line would be straight up and down, and the constant enthalpy line is straight up and down. That's where. Well, it's hard to see when you start changing axes, but that's the same concept. It's the same concept. You're right. Yeah, it's hard to see at times. So thank you for the opportunity to explain a difficult concept. How's that? So now, let me do this. I'm going to pause right now, and I'm going to hand you a print out of this diagram. And as a design engineer, you need to explore thinking about having two heat exchangers, a compressor, and an expansion valve. And you want to explore how high a pressure you push it to. Because you have the low pressure side. Let's say it's already dictated. The low pressure side is 300 psi. Because our evaporator, we want it to be absorbing heat at 0 degrees F. Okay? The condenser doesn't look like it's going to even be a true condenser. It's going to be a heat exchanger where you're going to be exchanging heat, but it's not condensing. And it's going to be a very high pressure. And so what I want you to do is explore for me how to draw that box. See, if I go back here and I say, what does a typical vapor compression refrigeration system look like on a pressure enthalpy diagram with the dome like this? Well, if I have refrigerant 134A or some other refrigerants, I'll be down here, I'll come across, I'll go through the compressor, this is state 1, through the compressor, S equal to constant, I'll stop somewhere, and then I'll condense at constant pressure. Now this is not condensing, but once I hit saturated vapor, I go and I condense all the way over to here, and so that's state 1, state 2, state 3, and state 4 is directly below it. There you go. See, so when I come into the evaporator at state 4, I don't have quality of 0, I have quality of 20, 30, 40%, whatever the quality is. True? So take this concept and try to sketch on this diagram that's generated with RefProp that I'm going to give you a copy of. Sketch what type of pressures we need for the high pressure side and what type of pressure we need for the low pressure side. We still only have high pressure and low pressure. Okay? So I'm going to pause and then pass this. All right, so one of the things you can do is you can go ahead and print. I'm going to go ahead and print this Control P. And when it prints this, it puts it into a file, which is nice. And I'm going to call this RefProp 3. And then I can mark it up, okay? So if I come over and put it into a journal file, and it just showed up right here. So this is what I printed out for you. And so we know that the one heat exchanger is going to be around 300 psia. That's going to be the low pressure. And let's say we come out of that at 0 degrees F, right? In saturated vapor, kind of doing the traditional compression system. And let's throw it up there, go way up to, when do you want to stop heating it? When do you want to stop compressing it? When the outlet is 300, when the outlet's 260, when the outlet's 220. Here's the outlet is 200 degrees, right? Isn't that the line of constant 200? Let me count. 200, 20, 40, 60, 80, 300. Right, that's a line of constant temperature of 200. Let's stop it when it's 200 and it looks like it's isentropic. What's that, right there? Did I do that okay? What pressure is that? It's quite high. It's up in this ballpark. This is 2,000. You have to read this diagram, but it looks like it's what? 1,400 psi? And if you then cool it and it'll cool until you get to a temperature. It can't cool any below, what did we say, 140? It can't cool below 140. It has to reject heat to the outside. And that reject heat means it's 15 degrees hotter than the hottest August day at the roof of a building in San Antonio. So we just assumed it was 125 roof air temperature, 15 degree. So it's 140. So I have to stop when it gets to, okay, 180, 160, 140, right there, true? Okay, now what do I do with this one? I want to put it through the expansion valve and do isenthalpic expansion, which is a straight line down. I got myself a problem. I didn't get way over here where I have a high, a quality where I can get a lot of evaporative cooling with this CO2, did I? So what's the remedy? What's my design choice to do with this CO2? See, I was starting with state 1 here, and I went to 2 there, and 3 there, and then 4 is isentropic, constant H expansion below, back to the low pressure. Ain't going to work, is it? So what's the recommendation? You can make CO2 work, but keep going, higher pressure. That compressor is not going to have to just go from 300 to 12 or 1400. Let's keep boosting it. And that exit temperature out that compressor is going to get really hot. Let's say it goes all the way to 300 degrees F. Do you want to touch that? Do you want to touch that outlet to the compressor? No, you don't. Okay. Now the high pressure is, let's say, above 2000, right? And now we're going to go and cool it by 20 degree increments, 20 degree increments, all that. And we're going to be able to cool it until we get over to this temperature, that same temperature at the previous state 3, right? So that temperature was what? What did I say? 140? 140, okay? Now if you can cool it such that it's 120, that's even better. But this ice machine better work on the hottest day in August. And you know what they're going to do. They're going to take it and they're going to move it somewhere to where it's even hotter. They're going to put it somewhere in Mexico when it's hot, or somewhere in South America on the equator where it's really hot, right? Okay? Or somewhere else. So now if I'm at state 3 there and I put it through an expansion valve, where does it go? And now what is my quality at state 4? Yeah, 60, 70%, which means I'm only getting cooling on about 30% of the mass flow. 70% is going for the ride. How can you get more? Well, let's stop here and make the analysis, okay? So do me a favor, write down some numbers here. We're going to assume that it comes out at state 1, 0 degrees F is saturated vapor. Make a note of that because I'm going to ask you to remind me of that, okay? And then what we're going to do is we're going to do constant S isentropic compression so that S2 is equal to S1. And we're going to do that up until the temperature is at T2, 300 degrees F. True? Then whatever that pressure is, it looks like it's over 2000 psi. We'll have to figure out what that pressure is. We'll do constant pressure cooling all the way to state 3. And what is the temperature at state 3? 140 degrees F. True? And then from 140, we're going to come straight down to state 4 isenthalpically such that H4 is equal to H3. True? Okay, let's do this. RefProp also runs in Excel. And I covered in the 8 o'clock, and it took me 15 minutes to show you how to upload and get it all linked in properly to run it in Excel. So instead of spending 15 minutes, just say, the instructions are there, you could follow them, let's jump to Excel and see what we can do with this substance. Where's Excel? Right there. Okay, so we're going to go state 1, state 2, state 3. We're going to be using CO2, carbon dioxide, as our refrigerant. So let's just say that my refrigerant is CO2. I'll put that there, and then I'll have state 1, 2, 3, 4. True? And we'll talk about pressure and PSI-A. We'll talk about temperature and degree F. We'll talk about enthalpy and BTUs per LBM. We'll talk about entropy in BTUs per LBM F or R, either one. I think probably R. Leave it R. Come on now, type. Okay. Do we need any more? We could put quality there if we need it. Just X. Okay. So we're starting at 0 degrees F. True? And we're starting at saturated vapor, so the quality is 1. Okay, saturated vapor, temperature, and sat vapor. That tells me what that is. So what is PSAT? P-S-A-T, and it's trying to give me the functions that have been built in. Okay, maybe I need pressure right there. Okay, so now this is pressure. It's a function that is in the Excel version for RefProp, and they don't give me good help. I wish they did. They didn't. But the fluid name, I'm going to click right here, CO2. Now the input code and then the units. The input code tells me what is my prop 1 and prop 2. All right. I'm going to do this, and I'm going to guess that pressure and quality will work. Okay? Now it starts to tell me I'm missing some inputs. That's fine. And I'm going to say it's English units, because that's our BSI and degrees F and BTUs. And our first property is our pressure. And so where is our pressure found? Temperature. Temperature in degrees F. So where is our temperature found? It's found in cell, that didn't work so hot, E5. Isn't it in E5? Yes. And then the quality is in cell H5. And so I can just click that cell H5. Now it says invalid input code. It probably doesn't like temperature and quality. Temperature and big X? Do you like that? No. Oh, please. How about this? Does it like CO2? Whoops. Input, no good. Well, that turkey. Let's do this. Let's see if we can't find pressure. Oh, man. This is always embarrassing, because you got to remember all of these individual, and they don't give you very good help. How about this? Pressure. Go to quick Google search. Where do I have it? PL. But this is the built-in from the University of Alabama. Oh, turkey. How about if I just assume it's 100? And let's see if I can get the enthalpy of, need a Y, PY, enthalpy of CO2 at this, as a function of pressure, temperature, for English units, for this pressure and this temperature. Let's see if that's going to work. It does work, okay? Let's do this. Quality of CO2 as a function of pressure, and it's not going to be independent, is it? Pressure and enthalpy. I'll try to fool it. and then pressure and enthalpy, and close paren and see what they get. Density iteration for single phase state did not converge, so it's in the two-phase region. It doesn't like that, okay? But what we'll do is get the entropy. So I come out slightly superheated. That's probably what I'm doing. The entropy for CO2 as a function of pressure and temperature, English units. There's my pressure value. There's my temperature value. And good, that works. So forget about X. Well, I'll come back to X later for state 3. So now we're going to push it out. What comes down? S comes down. Whoops. So state 2 is fixed by a pressure and an entropy. What pressure do you want to push it out to? Or did we want to do temperature entropy? We could do temperature entropy. That may work. Temperature entropy. See if this will allow it. So the temperature we wanted to go out to 300 degrees. All right, let's see if this is going to work. Enthalpy as a function of temperature and entropy. I've got to sneak that under. Oh boy, I just messed that up. I'm used to the syntax with the other software. I've first got to say what substance do I have, comma, what units, temperature, entropy, true? Temperature, entropy, in English units, and there's my temperature and entropy value. And everybody, what do you think? Going to work? It worked. Wow, that's great. Now let's go out to the pressure. So we have pressure for what substance? It's a function of temperature, entropy, English units. You get tired of typing all this, don't you? And then you just bring in that, comma, entropy, close. So something says that it's only less than 1,000 degrees F with that S. Huh. I wonder why. It looks. Can you tell me? I'm sorry? Oh, we're supposed to be 300, aren't we? There we go. Now it looks better. Now it's over 2,000. Thank you for that fix. Thank you very much. Now, what about state 3? Pressure, and we're bringing it to a temperature, true? So the pressure is this pressure, and the temperature, we brought it to what did I say? 140, okay. And so now we have to get the enthalpy of this substance, CO2, comma, given pressure, temperature for English units. Here's pressure, here's temperature. I do think it's a little better that it doesn't require your syntax always be cap E's or cap P's, or you see me put a lowercase e, lowercase or uppercase e. That works. Now I can get that entropy there. It's going to be lower, but we're not going to need it. The state 4 is the pressure and the enthalpy. True? Yes. The compressor is the best compressor we can have. It's adiabatic. Now, if the compressor has some cooling, then S will be lower. But I'm just assuming adiabatic reversible compression. Okay, let's do this one. We're back down to 300. And we're going to do constant enthalpy. And so I want to find the temperature. What do you think that temperature is going to be? Around zero. Around zero. So it's equal to temperature, tab, for my gas CO2, knowing pressure enthalpy for English units. My pressure is this value, and my enthalpy is right underneath. Tuck it in, close paren, and it's right at 0, negative something, right? Okay, let's clean up our units a little bit. -1 degrees. Okay, now this is where I could be interested in quality. Quality for this gas, knowing what is it, pressure and enthalpy for English units, pressure here, enthalpy there, and do you think it'll work? Good luck. It worked. Who said around 60-70%? You have great eyes. That's tremendous. That is tremendous. That's the quality at stake. So let's do this. What is my Q in the lowercase q in the evaporator? I'm still going to call it the evaporator, right? So what is the heat addition per pound mass going through the evaporator? What is that equal to? H 2, no, not 2, H1 minus H4. Agree? So that's how many BTUs per LBM that are picked up. Too many digits here. Come on, clean that up, please. Let's clean this up a little bit. All right. Now, how much heat per unit mass is rejected in the condenser? I know it's not condensing, but we'll call it the condenser anyway. H2 minus H3. So that's the same units, BTUs per pound. Okay, what about the work in the compressor? What's that equal to? H2 minus H1, and that's the same units, BTUs per pound. Now, what is the coefficient of performance for this refrigeration system? It's how much cooling we get per the work input. True? So the cooling divided by the work input. Are you impressed with that COP? 0.99. What do you think? Probably not so good. Let's do this as comparison. Do a copy. Oops, cancel that. Copy. Do a paste. Let's do refrigerant 134A. True? And notice it balked a lot because it does it like these pressures and stuff. But 0 degrees here is probably not 100 psia. Let's quickly jump back and find out. I'm going to do a new plot, change the substance. Substance. Do they let me do 134A? Good job. Okay, good. Now we're going to do a new plot. We'll do a pressure enthalpy diagram, and I'm just going to, I'm just going to run these values. Hold it. I don't want to go up to 500. Why so high? I don't want to go so low. What was our low temperature? -40? -40 and increments of 20 for the temperature. True? All right, let's just see what they connect up with here. Boom. Okay, so if I wanted to absorb at, and I've got to go a lot lower on my pressure. Let me replot that. Pressure enthalpy. Where's my pressure? X is right here. I've got to go down to, I don't know, 5 psia. And there's no sense going up that high. Let's do 10,000. All right. So there's 10. That's -40. So here's -20. Here's 0. So there we go, right? So what we want to do is we want to say, okay, it looks like the pressure is going to be about 20 psi. True? And what about if I'm rejecting it at did I say 140? Did I say 140? The high pressure, try to remember these numbers. is around 240 psi. That's a big difference, isn't it? A much big difference. So what is it again? 20 and 240. Let's go back to this Excel spreadsheet. So it's going to be 20 and 240. Oops. Escape. I needed to stay with temperature S. So let me do that. Let me go back to my plot. Okay, 0. I'm going to compress it isotropically until it comes out to right in this vicinity, about 180. Looks like I'll go out to about 180. That's my guess. Okay. So let's go back to Excel, and temperature of 180. Did that work? Let's get rid of these. Boom, 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 boom. It's still pretty high. Maybe I don't need to go out that high. 160. Here, that looks more reasonable, okay? Looks more reasonable for the pressure. Didn't I say the pressure was around 250, 260? Okay, here, 175. You want to split the difference or something? But this is good enough. And so using refrigerant 134A, our coefficient of performance, first of all, our pressures are much different, aren't they? Much more reasonable. Let me do this. If I have a leak in the evaporator, the pressure is 20 psi in the evaporator. Is the fluid going to come out or air going to go in? Refrigerant's going to come out. But there's only a 5 psi difference. So it's not going to be a bad leak, you know what I mean? Not like spraying and killing people. But look at this. I got 300 psi. If I have a leak there, it's really going to gush out, right? And now this is a lot higher pressure right in here. I mean, that's ridiculously high pressure. All right. So this is reasonable pressures. It's going to be a lot easier to seal it, maintain the seals with rotating machinery or penetrations through the seals. And you have a lot better coefficient of performance. We're pulling heat out at 0. We are condensing it. Look at that, 140. True? Isn't that at 140? What is the it's temperature, temperature. I should look at where this is on the state. Maybe this is completely bogus. I should spend some more time in it. Sorry, guys. Let's put this up to 250. There, maybe that's a little better. What is the quality? I gotta scoot over here. I don't know if that's going to be defined. Nope, not defined. Oops, maybe that's why it's not defined. Subcooled liquid. So it's coming out subcooled liquid at that 250, okay? You can see they're saying, hey, it's subcooled liquid. Quality's not defined. So it's slightly subcooled. Okay? So this looks pretty reasonable. Coefficient of performance is nearly double. You're going to have to spend a lot less electricity for the same amount of ice making that you want. Okay? And you're not going to have these ridiculously high temperatures, 300 degrees F, and not have the high pressures. Okay. So RefProp, you can do a lot of exploring